Hello students, we'll continue with Guided Inquiry Worksheet 3. This is a continuation from Worksheet 2, so you will need to have Worksheet 2 with you side by side so that you can reference to selected portions. Okay, so right now we'll look at the one in the box. Okay, so over here you were told that the rate equation. Okay, so the rate of a reaction is found to be proportional to the concentration of a reactant raised to an appropriate power. These are usually integers, but not always the case. Okay, so usually the one you encountered for A levels is 0, 1, or 2. Yep, but fractional order is possible. Negative orders are also possible. In fact, in most of the cases you will encounter in real experimental conditions, or rather in real life scenario, other than the common reactions presented to you in your exams, the order of reaction tends to be a little bit complicated. Yeah, they are either fractional or they are negatives. Yeah, so that also tells you that later on, if you move on in the topic, you will notice that the mechanism, because the order of reaction gives you an insights into the mechanism, meaning stepwise what happens at a molecular level. So in a lot of cases at a molecular level, the reaction is not as straightforward as you would perceive it to be. Yeah, so reaction kinetics, after finding out the rate law, it gives you an insight into the possible mechanism that takes place at a molecular level. So it is as though you have a very slow camera, yeah, and the camera is able to take multiple time frame of a reaction so that you can see what exactly is happening at the molecular level when the molecules collide, and what bonds are broken and what bonds are formed. But in reality, molecules are not spheres, you know, and bonds are not rods, so you can't really so-called visualize it at the molecular level. All the visuals you see on YouTube or animations, they are all fake, meaning they are there just to make the reaction seems more, you know, palatable to the eyes. Yeah, but at the molecular level it doesn't happen that way. Okay, yeah, so moving on, they give you this rate equation. So assuming that there's only one reactant, so R is raised to the power of X. So X could be usually any integer. Okay, so usually 0, 1, or 2 at the H2 level, but as I mentioned, can be fractional order, can be negative orders as well. Okay, then normally in order to find out the power, which is the X term, right, you will have information. You will have the following information. So you will know the initial rate of 2 and 1. You will know the initial concentration of R in 2 as well as 1. Okay, and you know that when you divide them in this fashion, the K will be cancelled off. Yep, so you will get a number here and you equate it, and you get another number here, and then after that you can either take a log, or you can do by inspection, and you can find out what X is. Right, yep. So this relationship between the rate of reaction and the concentration of reactant is known as the rate equation. So normally is written in this form. For at the H2 level, most of the time we write it out as rates. Yeah. If you move on to university, or some of you doing chemistry Olympiads, you will notice that the rate is often given as d concentration term over dt. Yeah, so it's, I mean, if you want to write it that way, it's fine, but at the H2 level, usually we write it as rates. Okay, so in the case of the reaction earlier on, if you remember, that is worksheet 2, right? We are looking at the reaction between iodides and peroxydisulfides. Okay, so we are looking at this particular reaction. So yeah, so it's only between these two terms. One is oxidizing agent, which is peroxydisulfides. The other one is iodides, reducing agent. So when they collide together, if you vary the concentration of either one, it will affect the overall rates. Yeah, so because we don't know the order yet, or the power term, so we let it be X and Y. Okay, K is usually the proportionality constant, known as the rate constant. It is usually temperature dependent. Okay, So it's only temperature dependent. The rate constant can only be determined by the experiment. So you cannot determine the rate constant simply by guessing, yeah, as well as the order. So these two terms are only determined through an experiment, and then you compare. Okay, then with that short introduction, we'll move on to question 1. So question 1 asks you to base your answers to question 5 and 6 from worksheet 2. Determine the order of reactions with respect to I minus and peroxy disulfate. So based on what we saw earlier on, okay, so let me look at question 5. Okay, so you notice that, okay, so we just compare experiment 1 and 2, huh? So for 1 and 2, you notice that when you go from 2 to 1, when you double the concentration of iodides, keeping peroxy disulfate constant, the average rate of reaction kind of doubles. Okay, and the same thing goes for peroxy disulfates. Okay, when you compare 1 and 3, and then you keep iodide a constant, when you double the concentration of peroxy disulfates, the average rate doubles. Okay, so because of that, from here we will be able to determine that the order of reaction with respect to iodide is 1. Okay, can. So this one, the order will be 1, and peroxy disulfates will be 1 as well. Then based on your answer to question 1 above, write the rate equation for the reaction between iodide and peroxy disulfate studied in worksheet 2. So what we're going to write would be rate is equals to the rate constant I minus raised to the power 1 and peroxy disulfates raised to the power 1. Okay, now I purposely write 1 over here, okay, just to impress upon you that the power is actually 1, but in reality you do not need to write 1. Okay, you can just leave it empty. So if you leave it empty, we assume, it's not assumed, I mean, you know that it is raised to the power 1. Yeah, so you don't really need to write the 1 there. But for teaching purposes, I tend to write it out just to impress upon you that the power term is 1. Okay, then from your data in table, in the table in question 2, from worksheet 2. Okay, so table 2 from worksheet 2, table 2 from worksheet 2, I think should be this particular table. Table 2 from worksheet 2, I think should be this. Calculate the value of the rate constant K, deduce its units using values from experiment 1. Okay, so what we're going to do here is we're going to repeat the same thing 3 times. Okay, so for experiment 1, experiment 2, and experiment 3. Okay, so what we are, okay, I'm just going to show 1. The rest of the working will be the same. Okay, so I will use experiment 1 as an example. So in this case, the average rate is 1.56 times 10 to the power minus 5. Okay, so I'm just going to use this equation. So 1.56 times 10 to the power minus 5. This is equals to rate constant. Then the concentration of iodide is 0.12. Okay, then the concentration of peroxy disulfates is 0.030. Okay, then after that I will make K the subject, and then I'm going to punch my calculators. I'm going to get numerical value 4.33 times 10 to the power minus 3. Okay, then right now I'm going to do dimensional analysis or unit analysis, okay, to find out the units for the rate constant. So concentration term is moles per dm cube. Okay, then another moles per dm cube. Okay, it's basically moles per dm cube squared, and the rate term here, okay, is moles per dm cube per second. Okay, so I'm just going to, so this term is going to cancel out. Okay, then so the rate constant is here, so I'm just going to move the term over. So this one I'm going to move over. So because I'm going to move over, right, it will be the reciprocal of moles per dm cube. So it will be moles to the power minus 1 dm cube, and then per second will remain. So this will be the units, and this is how we derive the units. Alright, Then I'm going to perform the same calculation 2 times, experiment 2 and experiment 3. Okay, I'm just going to punch the calculators. For experiment 2, I'm going to get 4.48 times 10 to the power of minus 3 per mole dm cube per second. For experiment 3, I'm going to get 4.21 times 10 to the power of minus 3 per mole dm cube per second. Comment on all the answers, right? So okay, so if you look at the rate constant from all the experiments, you notice that it is approximately the same. Yep. So if you have done the experiments properly and do the calculation in the appropriate manner, you'll notice that they will all converge into a similar value. That is why it is called the rate constant. Okay, right? Then next we'll move on to question 4a. When determining the order of reaction, we should compare initial rates instead of average rates of the concentration of reactants. Okay, why is this the case? Okay, so so if you look at the focus here, we should compare initial rates instead of average rate, right? With the concentration of reactant. So why is this the case? Now, as you might be aware, or it might be a little bit obvious, but it's sometimes difficult to discuss. If you look at what we are using here, right? I'm going to highlight this and this, right? These are what we call the initial concentration. Okay, right? They are called the initial concentration. So because they are initial concentrations, it makes sense to use initial rates when we are doing the comparison, but not the average rate. This is because as the reaction proceeds, the reactants gets depleted. Yeah. So unless you are able to tell the concentration of the reactant at that point in time, but even so, you should not be using average rate. You should be using instantaneous rates. Okay, but in our case here, we are using average rates. Why is that the case? Because as we mentioned in worksheet 2, the extent of reaction is very small, so the average rate is a good proxy to the initial rates. Okay, so I think we have to bear that in mind. I hope 4a will not be a confusion for some of you. They are really asking you average rate when the reaction occurs over a relatively longer period of time when a substantial amount of reactant has reacted. Okay, then for 4b, I think it might be a repeat again, so let's read the questions. In the experiment between I- and peroxide disulfate that was performed, average rate could be used, okay, or regarded as the initial rates. Okay, so the reason I've explained in 4a suggests why average rates rather than actual initial rate are determined experimentally. Okay, so again, it is more convenient to use the average rates in this case. Why is that the case? Okay, because number one, the extent of reaction is very small. I think in worksheet 2 we have done the appropriate calculations. I think it's about 0.8% or about 1%. So the extent of reaction is very small. So because of that, the average rate is a good proxy to the initial rate. Then number 2, we are using a fixed concentration of thiosulfate. So that fixed concentration of thiosulfate will be able to tell us or will be able to sort of inform us that when we compare across all the experiments we are dealing with, we are dealing with the same amount of iodine that is being produced over that short period of time. So therefore, it is a good proxy. We are not looking at varying concentration of iodine being produced. Okay, right? Yep. Then okay, then how do we then determine the initial rates if we really want to do that? Okay, so if we really want to do that, then what we need to do is we need to have the concentration of an appropriate reactant. Okay, and then we need to plot it against time. Okay, it can either be reactant or maybe in our case here, maybe it's a product because we are looking at iodine, right? So maybe it's iodine here. And then we need to plot over across all the points, okay, for all the experiments. So every experiment we have to, track the amount of iodine produced at every juncture. Then we draw a curve. So assuming that this is experiment 1, okay, then we can then determine the initial rates. Okay, so initial will be like this. Okay, so I'm not so okay. So this is the initial rate for experiment 1. And then if you want to draw for experiment 2, okay, so you repeat again. Okay, then you draw a curve, and then after that, okay, so after that you draw your straight line again. Okay, and then you will determine the initial rate. Now you notice that this is actually a very tedious process, because number 1, for each experiment, how long do we take? Even if we measure the intensity of the iodine, every experiment will take at least, say, 15 to 20 minutes. And then I still need to plot them. Okay, so we can use technology to help us do the plotting, and then we need to draw the best fit curve, and then after that determine the initial rates, and then after that compare the two. Okay, you compare this with the clock reaction, which you have seen in experiment 2 in the video I show you. It takes place probably less than 1 minute, and then it's because the amount of iodine produced is very small, the average rate is a good proxy, so we save a lot on the time. That is very important, and you need to recognize that. And probably this part is one of the most important area of kinetics that sometimes it's not well understood, and that's why most of students will have issues when they move on to JC2. Okay, right, let me move on. Next little box. So we have 6 reactions. Following table shows some experimentally determined rate equations for 6 reactions. Okay, they're all shown here. Okay, I think we need to, maybe I shouldn't introduce you to this term called elementary reaction yet, but basically all the reactions here are the overall balance equations. Okay, so you notice that for reaction 1, the power is the same as the stoichiometric ratio. Okay, for experiment 2, reaction 2, the power is also the same as the stoichiometric ratio. For 3 is the same, right? Yeah. For 4 is the same as well, right? But for 5 and 6 is different. You can see that the power is not the same as the stoichiometric ratio. Okay, for 6 as well. You can see that this is fractional order. Okay, then so for question 5, you are asked to study the information in the table above, work out if the order of reaction respect is always equal to stoichiometric ratio. So the answer is no. Okay, so 5 and 6 tells you otherwise. That also means one thing. 5 and 6 is likely to occur in more than one step, or what we call more than one elementary steps. Yeah, so therefore it may involve several different collisions, maybe collision between 2 reactants to give you an intermediate product, and then the intermediate product will then collide with the reactants. Or it could be the intermediate product will collide with another intermediate product to produce the products. Yeah, it can be very complicated. Yeah, so you encounter some of this in your H2 journey, but not too much, because again, if kinetics is too complicated at the H2 level, it's very difficult to frame the question. Okay, so but we're not saying that it's going to be easy. As I mentioned very often during our tutorials, kinetics is one of the most difficult topics you will ever encounter, and you might think that you understand it at JC1, but sometimes you move on to JC2, you will have new realization. So let it be. I mean it's perfectly fine. Okay, so finally let's do a short practice. November 96 all the papers. Okay, so this is a very simplistic question. You can see that all the data are very beautifully represented. Okay, so you have initial concentration for 3 terms, H2O2, I minus, and H plus. This is an acid catalyzed reaction. Okay, just for your information. And of course, most importantly, you'll notice that the concentration of acid is much greater than H2O2 and I minus. This is very important. And then you are given the initial rates for every experiment. Okay, then next, question A, determine the order of reaction with respect to H2O2, I minus, and H plus. So they give a sample for the working here, so I think it is important maybe to follow it this way, especially if you are not very good in writing. So if you use the mathematical approach, it will help you showcase your answer in a clearer manner. Yeah, the reason is because if you try to write it in a statement format, right, you may forget to write certain things. Okay, so let me just use one example. Let's say for H2O2. Okay, so for H2O2, I'll just give you one example here. So we'll follow the same working here. So we'll do rate of reaction 2 over rates of reaction 1. So we'll use these two. Okay, because these two are kept a constant. Okay, so I'm going to have 6.0 times 10 to the power minus 6. This is the rate of reaction 2 divided by the rates of reaction 1 times 10 to the power minus 6. Okay, then the rate constant. This is K, right? And H2O is 0.030. Let's say I raise it to X, for example, and then I minus and H plus, they are the same. Okay, Y, and then 0.10 Z. Okay, so I'll do the same. 0.010x, 0.010 y, and 0.10 z. Okay, then this is going to cancel. Everything's going to cancel off except for the x term. Okay, I'm going to cancel this. I'm going to get 3 here. Okay, and then I'm going to get 3 to the power x. So therefore, x is equals to 1. Okay, so the order of reaction respect to H2O2 is 1. Okay, so I think mathematics is quite straightforward because I just need to formulate the equation, show the substitution. Let me emphasize the term. You need to show the substitution. If you want to do the cancelling, please do it. And then after that, show that you determine x is equals to 1. But if you don't want to do calculation, what can you do? Can you write in this format? Yes, you can write in this format if you want. But it's a little bit tedious because you have to remember one thing. You have to emphasize that the concentration of I minus and H plus in this case is kept a constant across the two experiments. Okay, so I'm just going to maybe verbalize what you should be looking at. Okay, so you should write it in this format. Comparing experiment 1 and 2. Okay, when the concentration of H2O2 is triple, okay, it's tripled from 0.03 to 0.010, okay, keeping the concentration of I minus and H plus a constant. Yeah, this is a very important statement. You need to highlight that the concentration of I minus and H plus are kept a constant. Okay, then you after that you mention that the initial rates of formation of iodine tripled as well. Yeah. So therefore, the order of reaction with respect to H2O2 is 1. Yeah. So you have to write in full, which sometimes it can be a little bit tedious. Okay, some people may not like to do it in that manner, but it's really up to you. Yeah. So in most cases, I prefer the mathematical approach because it's cleaner. Okay. Yep. Then we're gonna do the same thing for I minus. Yep. But now I just verbalize it so that it's maybe easier. To discuss. So for the case of I minus, I think simplest way is we'll look at experiments 2 and 3. Okay, because H2O2 and H plus are kept constant. Okay, so what's going to happen is when the concentration of H plus I minus doubles from 0.01 to 0.02, the initial rate of formation of iodine doubles. Yeah, so because of that, the order of reaction with respect to I minus is 1. Okay, then can we look at experiments 3 and 4? So for 3 and 4, you notice that these are kept constant. Okay, then concentration of H plus doubles, initial rate of formation remains the same. So the order of reaction with respect to H plus is 0. Okay, so therefore it's 1, 1, 0. Right? Okay, then what is the overall reaction for this reaction? Okay, so if I look at it this way, the overall reaction, overall order is 2. Okay, because the overall order of a reaction is the sum of the individual order with respect to the reactants. Okay, then rate equation is simply rates is equals to rate constant, concentration of H2O2 raised to the power 1, concentration of I minus raised to the power 1. Okay, calculate the rate constant for this reaction, include its units. So you just choose, maybe I'll choose experiment 1 and I'll do the working here. So if I'm going to choose experiment 1, this will be 2.0 times 10 to the power minus 6. Okay, so this is equals to k, okay, 0.010, 0.010. Okay, then k is equals to, I'm going to bring this over here, so this will be 10 to the power minus 4, so I'm going to get 2.0 times 10 to the power minus 2. Again, it's the same. This will be mole squared dm minus 6, then this will be mole per dm cube per second. I shift it over, I'm going to get per mole dm cube per second. Okay, per second. Okay, right, so this is the way to do it. And if you are going to determine the rate constant, you can choose any experiments you want. Okay, so with that, we have come to the end of the review for worksheet 3. The next review will be for worksheet 4.